going to be using our powers chart to solve equations. And the types of equations that we're going to be solving are called exponential equations. An exponential equation is an equation that has the x in the exponent. So what's going to happen is if you had a question like 3 to the x equals 81, you would go to your powers chart and say, is 81 a power of 3? So I go to my chart here in the column with the 3. Sure enough, 3 to the exponent of 4 is 81. So you could replace 81 with 3 to the 4. And then we're going to use a mathematical technique of observation. If 3 to the x equals 3 to the 4, what could x possibly be? It's 4. So that will be our strategy of using our powers chart to try to solve these equations. And we're going to need a lot of our exponent laws from previous years. So if we look at A here, 4 to the x equals 1 over 256. We're going to go to our powers chart and say, is 256 a power of 4? Yes, it is. It's 4 to the power of 4. So what we can do with that is we can now rewrite the 256 as 4 to the power of 4. But our goal, in order to use the observation technique, would be to have both sides as a power of 4. And in order to do that, you're going to have to use your negative exponent rule. Negative exponent rule says you can move something from the denominator to the numerator by making your exponent negative. So we're going to use our exponent laws from grades 9, 10, and 11 to manipulate both sides to get both sides as the same base, a single power of the same base. And at this moment, you can just go, so, since 4 to the x equals 4 to the negative 4, x would have to be minus 4. And we can just, by observation, say that that has to be true. For part B, the numbers that we have are 27 and 9. So first of all, we might go to our powers chart and look at the power of 9 and see, is 27 in that powers chart? No. Obviously 9 won't be in the 27 one either. So then we look at other columns and say, do the numbers 27 and 81 ever appear in the same column? And the answer is yes. 27 is 3 cubed, and 81, or 9, sorry, is 3 squared. So both 9 and 27 show up in the column in the powers chart with a base of 3. So we can take 27 and replace it with 3 cubed. We can take 9 and replace it with 3 squared. And now we have to remember our exponent laws for a power to a power. Do you add? Do you multiply? Do you subtract? If you forget some of your power laws, the best way to remember a power law is to take a simple example and just figure it out. For example, if I took 4 squared cubed, should I add? Should I multiply? Should I subtract? Well, think about, what does cubing mean? Cubing means repeated multiplication. Squaring means repeated multiplication. Does it make sense that 4 squared cubed would be 4 squared once, 4 squared twice, 4 squared 3 times, multiplied by each other? And 4 squared means 4 times 4, and 4 times 4, and 4 times 4. And if we look at that, we have 6 4s all multiplied together. The answer is going to be 4 to the 6th. And if I do that simple example, how hard is it for you to remember that you need to multiply? Once I've done a simple one, I'm like, oh, I could have done that quicker by multiplying. That's going to be important because here I have 3 cubed to the x. That will multiply. That will be 3 to the 3x. And on this side, I have a power to a power, so I need to multiply. And how do I multiply? I'm going to have to distribute, so it'll be 4x minus 2. And we get to this point where both sides are powers with the same base, so we're allowed to say, so 3x would have to equal 4x minus 2. If I move my x's to this side and my 2 to the other side, I can solve, and x is equal to 2. Questions you can circle on this one are 3, 4, 5, and 6.